Okay.
Forward.
Okay, great. Thanks. Okay, well, as Igor said, well, he didn't say all this, but we've been looking at this problem of diagnosing the state, the health, if you will, of underground distribution cables for a few years. And so what we'd like to do is to, in this talk, I'd like to present some of the approaches we've taken and some of the results we've gotten. One of the game rules in this was that these should be in-service cables, not ones where you've had to turn off, where the utilities have turned off the service to the customers. Another ground rule, which was kind of annoying at first, was that we were not to think of drilling little holes into the jacket around the cable in order to contact some of the things inside. We were also to focus on cables that are in the ground, because we learned, much to our surprise, that there are many, many miles of underground cables that sit there and work nicely for 15 or 20 years and then all of a sudden blow up. And so it's too expensive to replace all those cables with supposedly better cables, and so the desire was to find some information about the state of the cables that were there by not breaking these other rules of turning off the power or drilling small holes to contact them. So I'm going to talk essentially about four, I guess, approaches that we've taken. And I'll try to go through this fairly fast and maybe get you to lunch earlier and so forth. So this is a typical piece of jacketed distribution power cable with a center conductor with some insulation, shown sort of in yellow here. Then there's a semicon, which is a conducting plastic coating, and then on top of that are wires, copper wires typically, that wind their way down the cable, known as concentric neutrals. And then on the outside is a jacket, a protective jacket. So what we looked at were, as I said, four approaches. The first one I'll talk about is what's called interdigitated dielectrometry, which was begun, I believe, by Professor Mamyshev, and I've never met him, but I think he's here today. Is he here? Yes. I'll hope to meet you afterwards later. So that's, we're calling it ID for short. Another was to use magnetic field sensors and take a look at the currents in these individual concentric neutrals. And the goal there was to be able to find concentric neutrals that were damaged. Maybe they were broken mechanically, maybe they were corroded through, and therefore they weren't doing the job they were supposed to in the cables. And we have two approaches to that. One is to both of them use an anisotropic magnetoresistive sensor, commercial sensor from Honeywell. It's about 3 millimeters on the side, and so we could move it down the cable as in this linear direction and measure the currents in each of the concentric neutrals as that concentric neutral came by under the sensor, and I'll show you some of the data we got with that. We could also make a necklace of these things, put it around the cable this way, and also get measurements on all of the separate concentric neutrals. And then we also we're interested in some RF probing methods, two methods that I'll talk about. One is using a surface RF wave, surface guided wave. It has most of its energy outside the guiding structure, which could be either a conductor, bare conductor, or it could be a conductor with a little insulation on it. And it goes by the name of its inventor, Georg Goubau, who first came up with analytical and experimental work on this sensor back in 1950. The other RF approach is to make a transmission lines out of taking two of these concentric neutrals at a time. If you look at that from the standpoint of electromagnetic theory, well, that's a two-wire transmission line. And so we thought, well, maybe we can propagate some probing RF waves down the structure using the two wires, so the two wires of adjacent concentric neutrals. So I'm going to go through these various techniques and try to show you what we've done. We've also put on the slides the names of the students who are primarily involved in these particular projects. And that's important for you because they have posters outside that and they will stand by their posters at the appointed time. You can talk to them and get more information about their work. Also, I don't know if it was mentioned, but there's going to be a poster preview in which each of these people will come past the podium and give a 45-second summary of their work. So you get to know them pretty well by the end of the day. So Giovanni's been looking at this dielectrometry, and the idea there is if you play your cards right, you can have a structure where a probing electric field, this is maybe a good example, a probing electric field that's set up by energizing some conductors on the outside of a dielectric. If you adjust the dimensions of this correctly, you can get an evanescent field that sort of reaches inside the dielectric. And therefore, you could make some measurements of what the physical properties are of the dielectric inside there. Furthermore, since we're looking at in-service operation, if as the voltage on the cable goes through its cyclic variations, then the physical properties, the complex dielectric constant or the permittivity and conductivity in a damaged region might change and show some nonlinear behavior. Whereas if the cable is very healthy, then the properties would not change as you apply this electric field. So the idea there is if you can't turn off the power to make the measurements, use the voltage or electric field that's normally delivering power and try to interpret make these measurements, interpret the characteristics of the cable inside, the insulation inside. So Giovanni has looked at this from experimental standpoints. He's also done some analysis where he's shown that you can take a structure, let me back up. You can take a structure like this, a capacitor, which is understood nicely, and you can convert it, use an equivalent capacitance to represent this structure here. So you do a transformation, using elliptic integrals, and so he can determine the electric fields that one of those sets of conductors would produce. So this shows some of the structures, the electrode structures that he's made. He went into a rather unusual method of fabricating these things. The idea here is you start with some insulator that has some copper on it, and then you want to do some etching and leave these structures, and then you hook up to those, connect your probing voltage source to these, and lay one of these structures against the cable, typically between the concentric neutrals, the underlying concentric neutrals, and then you will produce a probing field that extends into the cable. He used a rather unusual fabrication means, I think because the dimensions here are much larger than are usually found in microfabrication. So I'm not going to go through this routine, but it involves printing his structure on glossy paper, doing some ironing for an hour. There are various things, and you can ask him about that when you talk to him at his paper. But he's made some of these structures and has made some measurements on dielectric slabs and so forth to verify that they can measure these properties. Thanks to Steve Boggs' continual suggestion, we're looking not only at permittivity, which we're focusing on initially, but also the conductivity in these insulators, because they may show more of a change than the permittivity. And I believe this plot shows the electric field intensity within a dielectric when you apply alternate voltages to these electrode fingers outside. This approach may be useful. Well, it's really useful only when the defects or the changed insulation regions are available, are accessible to you. And they are not accessible, of course, in the major length of the run. But one of the cable run. But one of the things we're thinking about is, well, if this is a good way to monitor the state of the insulation inside, maybe these things at some point could be built into cable. It's new cable that's going to be put underground. Okay, the second approach that I mentioned was trying to sense the currents that flow in these concentric neutrals. We've been told by the people in power companies that the state of the concentric neutrals is important to them in the functioning of the power line, the cables. And so we figured that we could actually measure the currents in individual concentric neutrals and hopefully interpret the results. And what you'll see is, I'm going to show you some plots of the data that we've gotten, and you'll see that things are complicated, but that suggests that looking at the signatures that we pick up this way may be diagnosing conditions inside the cable. So this shows a couple of setups. This shows the Honeywell magnetic field chip, 3 millimeters on the side. So it's small enough so it will fit it will give us spatial resolution when we're over a concentric neutral or we're in the gap between that and the next concentric neutral. These devices have the capability of measuring the magnetic field in 3 orthogonal directions. So if we have let's say we have a cable like this, and one of the students made the concentric neutrals visible by painting on them so he could tell where they were. Here's our mount for our magnetic field chip. And this is a helical drive to move this thing along the cable. And so we can measure the longitudinal magnetic field, the circumferential magnetic field, and the magnetic field that sticks out radially with this chip. And as you can see, as you move this thing, each concentric neutral is going to come by in its turn. Or if we had the necklace, then we could measure each one in one location. So we did that with a number of jacketed cables, but we kept hearing that the concentric neutral problems are really most extreme, most of interest when you have unjacketed cables for direct buried installation. And so we have some cable that we were given by one of the 3 IOUs in California. So this is cable that's not jacketed. It's been in the ground, and so it's somewhat corroded and so forth. And also, if you look closely, you'd find that in the process, I guess, of installation and removal, some of the concentric neutrals have bunched up in locations and so on. But I think this is probably a typical case. So here's the device that moves the magnetic field sensor along the cable, and these are the standard fittings that go on the ends of a length of cable. And so we've been putting current through there, either through the concentric neutrals as a group, or maybe through the center conductor and the concentric neutrals as a group, or on our jacketed cables, we've done some experiments where we probe when we open up one of these concentric neutrals, cut the concentric neutral to make a measurement, and then close that connection again and see if we can tell the difference. So the idea there is, can we make measurements on a cable in the ground where a little bit of it sticks out in a vault, make measurements along that segment and tell whether there are any breaks in the interior of in the CNs in the interior of the cable. Several people have been doing modeling on this. Professor Jim Evans has been doing modeling where he's added the effects of elementary magnetic fields from elementary currents flowing here. This is the concentric neutral. And Dr. Kanna, Krishnan, who's a postdoc, has also been analyzing these problems, and they get together with a couple of the students every week and compare results and look at the experimental data that's been obtained. This shows some of the data that you would find. Each of these three colors represents a different component of the magnetic field, and this is for a cable where all the concentric neutrals were intact, and this was a jacketed cable. And so you see the magnetic fields repeat with a nice periodicity of the concentric neutrals. This was done with the linear machine to look at the concentric neutrals as they came by. And this shows the results that were obtained when one of the concentric neutrals was opened up, and you see a very big difference, so you can tell very obviously this is a way to tell when these things have failed by, say, corrosion through that particular concentric neutral. This is either, you can look at this either as sort of a mess, or you can say it's an opportunity for looking for signatures that you could detect and interpret. These are results with, again, jacketed cable, and you see once again that this is one where either all the CNs were conducting or there was a break, and this shows that you can see very clearly a big difference when the magnetic sensor comes by the concentric neutral that has the break in it. This is another set of measurements. This is on about, I think, a 200-foot cable. There was a break in the concentric neutral about 3 feet from the source, RF source, and then these measurements were taken by moving the magnetic field sensor over the cable, starting about 3 feet from where the break was. So this would be like 6 feet from the feed point for that cable. And then the same measurements were made 100 feet away from the source, and you find that you can still detect which concentric neutral has been broken. And if you go to the end of this cable, which was 200 feet long, again, you can detect it. As you get further from the break, this becomes a little less prominent, but you can see it's a very clear indication that there is a break. And this is perhaps somewhat surprising because underneath the concentric neutrals is the semicon layer, which is highly conductive, but we are still able to detect the fact that there is a break there. We did this also with unjacketed cable, and as you can see, this was the cable as we received it from one of the utilities. It's kind of a mess. There are gaps here, things are bunched up, there's corrosion of different colors and so on. But we applied our magnetic field sensor here and moved it along here. And this shows the data of the three axes of magnetic field. And I think the one that's most easily noticed is the blue one here, which is the circumferential magnetic field. And if you notice from this plot, you can tell actually the spatial periodicity of the CNs, because one of them, there's a region where some of the CNs have slid from this region over to adjoining regions, so they're kind of bunched up here. There aren't many here. And as you look at this diagram, looking at the blue curve, you can see, okay, here's a signature of that. Same thing repeats here. Same thing repeats there. So the periodic distance where these things arrive is here to here, for example. And so there is the implication of a lot of information there. And these are fairly new data, so we're still in the process of trying to see how much information we can get out of that. Okay, then I'm going to turn now finally to the two RF probing methods. And the chief investigators on this are Dr. Paprotny and Dr. Krishnan, both postdocs in our group. So first of all, we're going to talk about, well, I guess we'll talk about both of them, but first we'll talk about the surface wave. So here again is our piece of cable, and the idea is to launch this RF surface wave, first analyzed and experimented with by Georg Goubau. So what we want to do then is to launch this wave, most of whose energy is outside the cable. And its energy is very concentrated. It's guided by the cable, but its energy spreads out quite a distance from the cable. As a result of that spread, where the energy is, most of the energy is located in the air, let's say, around the cable, this has very low loss per unit length. So the other RF approach then is to couple to say a pair of these concentric neutrals. Since we're forbidden from drilling holes into the jacket and making galvanic connection, we're looking at a capacitive scheme for exciting a pair of these and exciting wave propagation in there, from which we hope to be able to measure, if there's some damage, we might see reflections, and so forth. So we have those two approaches. I might also mention at this point, we'd like to thank the utilities for providing us with real cable, and not just real new cable, but also failed cable, so forth, and also some measurement equipment. For example, PG&E has loaned us one of their time-domain reflectometer boxes to make measurements in the conventional way that power companies do. So taking the Goubau wave, this is an idea of how it would be done. We'd have a transmitter at some point, perhaps capacitively coupled to the cable. And then what Goubau showed is that you can launch the wave by going from a coaxial mode to something like a TEM mode for free space. So his approach was to use some funnels, conducting funnels, to gradually change the impedance. Then you launch a wave, it can go along the cable, and you could have a similar detector on the other end. So this shows our first experimental setup in the recent years, where we have a green single conductor here with some green insulation on it, and a couple of funnels to launch and receive the Goubau wave, operating at some hundreds of megahertz. These first funnels actually came from a company called Sur La Table, but many of you may know that sell things to cooks. So, but they were just ideal for the purpose. More recently, as I'll show you in the next slide, Igor has made some funnels out of copper foil to better launch things. This may seem sort of weird, I mean, doing this sort of thing with funnels and so on, but there is a company called Corridor that has still in business and is using this mode to kind of solve the last mile problem, to bring video feeds down drop wires and so forth to houses, and again using this Goubau wave. I'm not sure where they got their funnels. I think they make them. Well, this shows a setup that we have in this building. So we have about 100 feet of standard distribution cable, and here are a couple of funnels, a launching and receiving funnel made by Igor out of copper foil. And so we've been looking at transmission along here, and then doing other experiments where we look at radiation and so forth, and we looked at the coupling efficiency of these funnels and so on. So this shows some results of measurements with galvanic coupling. So where we actually get hold of the conductors there at the in the region of the funnel. And then the next slide, I think, shows capacitive coupling results. So what we found with galvanic coupling is that we got pretty good coupling. So we put in 14 dBm, 14 dB above a milliwatt. And after 100 feet of propagation, we were getting something like, what is that, about 14 dB, I guess, of loss. So something like 28 or so dB attenuation in this 100-foot travel. And you can see the actual pulses. This shows the pulse that was inserted at the beginning of that 100-foot cable. And then this shows the received pulse, which was at the second funnel. And the time delay between these centers of these pulses was about 100 nanoseconds. And since light in a vacuum travels at about a nanosecond per foot, that indicates that the wave, that the Goubau wave is traveling, is a very high velocity wave, is traveling at nearly the velocity of light, which is as expected. Incidentally, the amplitudes of these were adjusted, so they both fitted on the screen. This was obviously, received pulse was obviously a good bit smaller. But you can see it's a good pulse, and we could do a lot with it. This shows the results of the capacitive coupling. What we did here to do the capacitive coupling was to put, I think, about a 5-inch long copper sleeve around the jacket of the distribution cable and drive that with a coaxial cable from the source. And all of this is inside the tube part of the funnels. So there we have non-invasive, non-galvanic coupling. And what you see here, again, this yellow is the source. This is the transmitted pulse, and it arrived at the other end of the cable after 100 nanoseconds, as expected. But there was also a pulse that arrived very promptly after the transmitted pulse was applied, the source pulse was applied. And this is, we believe, is radiated energy that went from the driving funnel to the receiving funnel because they were located somewhat near each other. But what you can see then is that capacitive coupling does work. There's something like an added loss of about 3 dB at each of these transitions, capacitive transitions, which is, I was surprised. That's not a lot of loss at this capacitive coupling. So it shows that we can do this kind of probing. Then the next thing to do is to see whether this wave interacts with discontinuities in the cable. So what we did was to look at the pulses with no breaks in the CNs, and then make some rather radical breaks in the CNs. That is, go to a certain length, certain position on the cable, strip off the jacket, and then cut 5-inch lengths out of all the CNs at that point. So we're really making a large break. And so this is the received pulse. Again, the input pulses are about the same. The received pulse here is somewhat less than the received pulse when there are no breaks in the CN. But at least this shows you can use this probing means to detect breaks in the CNs. In this case, it was a 100-foot cable, so in this, I think the breaks were about 80 feet long. So at some distance, you can detect the breaks using this RF probing means. Then this is taking a little further. This was with the 5-inch gap in the CNs at one location. This is with a 60-inch gap, so that all that's left in that region is the underlying semicon. And so you see that we do still get transmission, but the transmitted pulse is somewhat smaller than it was when we had just a 5-inch gap. And so our next step is actually to try the same experiment, taking away the semicon in this region here. And that should, I expect that this will do a couple things, that we will see less transmission and probably more radiation at that discontinuity. So we can, but still gain some information about the conditions of the cable at that point. And this is some data on the 2-wire transmission line. Once again, 2 wires meaning take 2 adjacent CNs, drive them plus minus, and again with an RF wave of hundreds of megahertz, and see what sort of propagation you get. I think it's fair to say we haven't really explored this mode of propagation all that much, but you do see differences between the case where you have no CN break and one CN broken a little ways down the cable. So we're looking at this sort of experiment, going to do more of these experiments, and just see how far away we could detect a break. These results did show that, again, we could detect a broken CNs 100 feet along a cable or 200 feet from the observation point, which is good news, since the cables are typically inaccessible for those regions. Okay, then to finish, what we've been looking at, what we've created, I guess, is a toolbox of online diagnostic techniques. Some of them, the interdigital dielectrometry sensor needs to be located at the site, and it looks at the characteristics of the insulation inside the cable by reaching through between the CNs. So one could think of possibly building those things into new cables, so one has some continual information about what's going on in there. In terms of remote sensing, which could be done by looking at propagation between 2 adjacent vaults, 2 cable lengths, or since utilities would prefer not to have to work at both ends of a cable, maybe just looking at reflected waves when you excite things at one of the vaults. So we're looking at the use of this magnetic field sensor to look at the currents in the individual CNs. We're looking at the use of the Goubau wave and also the 2-wire transmission line wave to look for changes that have occurred in the cable. And we have shown that these techniques, the remote techniques, do detect CN failure, and we get complex failure signatures, and we're working at trying to analyze the information content, see how much we can learn from about the state of the cables from those. So I'm going to finish by thanking a number of people. First of all, our technical advisory committee who were here, and Tony and Al, who are people at PG&E who have been very helpful in giving us cable and fittings and a lot of good advice about safety. Don't do experiments over 15 volts, things like that, which we're all still here, so we really appreciate that. And this work obviously could not have been done without the support of the California Energy Commission, which we greatly appreciate. All right, thank you.
When you remove the neutral wires, you essentially create a system with 5 transmission lines. On the source side, from the conductor to the neutral wires, from the neutral wires to ground. Then you have a segment from the conductor to ground, and then you go back to 2 transmission lines which are in parallel from the conductor to the neutral wires to ground. Has anybody done a thorough analysis of this? Because you're going to get some energy coupled that's going to come back between the conductor and the neutral wires. You're going to get some that goes in between the conductor and neutral wires, and you're going to get some outside. Of course, at 300 megahertz, anything that's between in the dielectric is going to be attenuated really, really fast by the semicons. But still, it's an interesting multi-transmission line situation.
It'd be a good to put on a qualifying exam or
well, if the gap's big enough, if the gap's large compared to the wavelength, then it becomes a relatively trivial problem. When the gap's not large compared to the wavelength, it's not something for a qualifying exam.
Okay. Now, I would think it's safe to say we're just looking at the results of the transmission with these breaks and so on. And one of the things we've done is to look at the signals that arrive at the end of the cable, but also to station an oscilloscope near the break with a probe and look for radiation, things of that sort. And so I think it's rich with opportunities for analysis and a good effort to see what we can get from this information. So.
It would be interesting to try to apply the EM propagation model in COMSOL and see if
Right. We are using COMSOL and then also MATLAB for the analyses, and so
yeah. We have the EM propagation model, but we never used it.
Okay, great. That's terrific. Thank you. So, any other questions? No.
Actually, I don't have a question, but I just wanted to add a little bit.
This is Dr. Krishnan.
Yes.
Who's responsible for a good bit of this work.
I just wanted to add a little bit. This may be at this point a little bit speculative, but this is kind of my analysis and my speculation, so I'll take responsibility for this. And basically the 3 different methods kind of do 3 different things. For example, the AMR measurement will show any uneven distribution of currents returning through the CNs. And the 2-line transmission method, basically what it does is, because the CNs are connected to the semicon, the signals attenuate very fast when you try to transmit through those 2 lines. So normally you'll have very heavy attenuation and you won't have any amount of significant signals. But if there is a separation between the CNs and the semicon, you will see a larger signal, and that's an indicator, and that is that's where the 2CN test is effective. And the third thing, again, is the Goubau method primarily looks at a combination of the CN and the semicon, because if either the CN is cut or the semicon is cut or damaged, for any reason, you will see a significant attenuation on the Goubau signal, and we are going to try that. We are going to try to cut the semicon and have a plot on that. So each of those methods, address 3 different things, and that's all I wanted to point out.
Okay, thanks, Kanna. I might just add to that. We've tried some experiments with some corroded CNs, that actually some copper wire that I found out in my backyard that I think came from PG&E and was heavily corroded. And we did some experiments with that, and when it's heavily corroded, that corrosion product, at least in according to our measurements, is a very good insulator. And so when the CNs corrode, they may be in physical contact with the semicon, but electrically they are isolated from it, and all kinds of interesting things happen there. So that's something, I think we might be able to model. So, okay. Thank you.